All right. Thank you for coming to today's Warren Lecture. Our speaker today is Dr. Seongjin Choi,
Choi.
approximately. Okay. He told me how to do it, and I forgot already how to do it correctly. All right. Seongjin got his PhD from Korea's Advanced Institute of Science and Technology in 2021. Spent a year doing a postdoc at McGill University. And in 2024, he started an appointment as an assistant professor with this outfit called the Department of Civil, Environmental, and Geoengineering at the University of Minnesota here. And he's doing his work in data analytics and deep learning. And he's come here to educate some of us statistical old timers, okay, on some new techniques here. So I'll turn it over to Seongjin.
Thank you so much for the great introduction. I'm not sure if I can teach the great audience here. And thanks again for Judy and Paige for offering this opportunity. Because I talked about this when I interviewed last year with Paige, because when I was preparing for the interview, I watched at least, I don't know, like 10 to 15 Warren lectures. So it's a great honor to me. So I didn't expect this time would come this fast, but then I really love this opportunity. So the title of today's talk is Understanding Distributions of Traffic and Mobility Data. So I'm going to talk about some recent advanced techniques that I can model, so researchers can model traffic data and mobility data and their distributions. So when we talk about data, nowadays it's in many of research, data is fundamental tool to analyze something. But sometimes people just call it data, but don't really understand what this data truly is. So we collect data from real world, and then we try to have some kind of model that from the data that kind of mimics the real world, but somehow simplifies the real world. But what do we actually want to do from this model? And what do we want to see from this model? And what do we want to build what do we want to build based on this model? So my understanding is the reason why we are building a model, developing a model, is that we want to generate synthetic new data. So we are trying to create synthetic virtual data. And then by doing so, we are trying to understand the real world. So let me give you a quick example in transportation engineering. So we can think of this as a real world traffic scene of a highway. The traffic engineers have developed a lot of different theories and models based on the real world collected data. We did some macroscopic modeling, microscopic modeling. And by doing this kind of modeling process, we build some kind of traffic simulation to generate, simulate, create, reproduce realistic behaviors or phenomena in the real world. And for the reference, these two simulations were developed by me during my master and PhD studies. So my definition of data is that I view real world as distribution, and I view data as samples from this distribution. And the act of our research and the act of us trying to develop a model is that we want to understand the distribution, the original distribution of the data from partial samples. So we want to understand and learn the distribution from the samples. And as far as I know, there are mainly two ways that we can do this currently in the state-of-the-art methodologies. First one is we assume a probabilistic distribution, and then we learn the parameters that's associated with the assumed probabilistic distribution. The second one is we train a neural network that can produce similar properties to the given data, or we can develop a neural network that can generate new synthetic data. And these two ways, these two methodologies, that's kind of it's the ways that kind of penetrates my studies, my works, my research from my PhD to postdoc. So I'm going to talk about deep probabilistic forecasting, deep probabilistic traffic forecasting, which was my postdoc work. And then I'm going to talk about generative trajectory analytics, which was my PhD work. So part one is deep probabilistic traffic forecasting. This was part of my postdoc work. I worked in McGill University. So first, let's kind of briefly define what traffic forecasting is. So formally, we can say that given historical observation XT, which is N by P matrix, where N is the number of sensors and P is the number of input horizons that's given to the model. Our objective, our target is to predict the future state of those traffic sensors, of the traffic variables, such as traffic flow, traffic speed at that sensor location over the next prediction horizon, which is Q. So we are trying to predict from this XT, N by P matrix, we are trying to predict YT, that NQ matrix. And this topic has been really really popular along in transportation engineering in the past 1 to 2 decades, because now we have access to a lot of data that's collected real time, and we have about more than 10 to 20 years of data of highway flows or arterial flows. So Caltrans PEMS is one example. We have data from Korea Express Corporation. Also, I just found out that MinDOT also has some data that counts the number of people passing or number of vehicles passing certain locations. And there has been some kind of breakthrough or shift of paradigm after machine learning and deep learning was kind of introduced in transportation community. So nowadays, from this paper from 2017 called DGRNN, people use graph neural network or gated convolutional neural network to model the temporal process, recurrent neural network or transformers, and then try to further predict the traffic state more accurately. And then we've seen this kind of converging graph from 2017 to 2024 that people have developed deeper and deeper, more complex and more complex, and more detailed structures that specifies that's specifically designed to solve or predict this traffic state. But now we are seeing some kind of this slowing down trend of the performance perspective. And then some people might ask, are we actually going to improve the model by just stacking up more and more neural network, adding more parameters to the model? Or do we have to kind of consider some kind of characteristics that's really in the data so that we can actually train a neural network or train a model that can really mimic or model the actual distribution of the traffic states or traffic data? And actually, that was the question I was trying to answer during my postdoc. So my main objective was that how can we further improve deep learning-based traffic forecasting model by using probabilistic approach and by leveraging spatial temporally related structures in traffic data. And I worked with this great team with Professor Lee Junsun from McGill University and Mr. Vincent Jing, who's a PhD student in McGill University. So we are trying to model the distribution of future traffic state. So we have to know how conventional machine learning models or deep learning models kind of treat this distribution of future traffic state. So when we want to know that, we have to look at the objective function or loss function we are using to train those models. So in most cases, the conventional traffic forecasting model kind of treat this as a deterministic spatial temporal forecasting, and then they use mean squared error or mean absolute error as their loss function. And so this is a multivariate Gaussian distribution where we have a mu vector and sigma covariance matrix. We can substitute this covariance matrix into with a diagonal matrix with fixed standard deviation. Then after some log likelihood, we can get this x minus mu square, which corresponds to the mean squared error that we are using to train traffic forecasting model. But this essentially assumes that the covariance matrix follows, so the distribution itself follows independent isotropic Gaussian distribution. And in the case of MAE, mean absolute error, we are assuming that the distribution is following independent isotropic Laplace distribution. But is this really true? So I had to look into the data to figure out what the actual distribution looks like. So this is a quick experiment I did with graph WaveNet, which is one of the widely used traffic forecasting model based on graph neural networks and deep learning. And I used PEMSDAY data, which is open source data collected in California, Bay Area near San Francisco. And I extracted some empirical temporal covariance and empirical spatial covariance from the predictions made from graph WaveNet. So this upper figure here shows the temporal covariance matrix. The lower figure here shows the spatial covariance matrix. I took data from 2 to 3 a.m., which is during the night. And we expect everything is free flow and everything is uncongested. And I took some data from 8 to 9 a.m. and 5 to 6 p.m., which kind of represents the congested period. So when we look at the data, we can actually see that, so in 2 to 3 a.m., we can kind of observe some independent like covariance matrix, but we see high, strong spatio-temporally correlated structures in 8 to 9 a.m. and 5 to 6 p.m. in both temporal and spatial covariance matrices. And then we also see that this distribution as a whole is a time-varying distribution. It's a dynamic distribution. So we cannot simply fit one Gaussian distribution to model this whole traffic data. So the objective of this study was to tackle this conventional deterministic setting of traffic forecasting has wrong underlying assumption. And we wanted to propose a new loss function or new objective function for training for traffic forecasting by using probabilistic approach. So here, what we are trying to do is to model the time-varying joint distribution of the residuals of the predictions. So we are trying to model this P RT given XT, where RT is the prediction error, which can be defined as YT minus MT, where MT is the mean of the distribution. And I'm proposing to directly train the model by using maximum likelihood estimation, which means that I'm using the negative log likelihood itself to train the model. So note that this negative log likelihood corresponds to MSE, as I mentioned, when we assume that distribution is independent isotropic Gaussian distribution. So I'm going to assume some kind of distribution for this P, and then I'm going to use this negative log likelihood and a LEL loss directly to train the model. And as the distribution I'm going to use for P, I assume that this is a mixture of Gaussian distribution. This kind of gives us some kind of theoretical background because Gaussian mixtures can ideally fit any type of distribution when we have large amount of number of components. Also, it kind of gives some kind of interpretability afterwards that I'm going to show in the results slide. So here, our data, RT given XT, we assume that it follows mixture of Gaussian distribution. So we have this omega t, which is the mixture weight, and we have the sigma k, which is the component covariance matrix. We assume that the mean is 0 because we have the MT subtracted from YT. And then we set this omega t to be time varying and sigma k to be fixed over time so that we can model the time varying dynamic distribution of traffic data but also we can have some kind of interpretability in the later result slide. So we can just directly put the equations into this negative log likelihood, and then we have this equation as our output. But here, the problem is that this inverse operation and determinant operation has a cubic time complexity. And we have to do this inverse and determinant operation over and over again during the training of the neural network. But this covariance matrix is NQ by NQ, which is too big to do even with the state-of-the-art GPUs we have out there. So for example, for PAM-based data, which has 325 sensors, and typically we set 12 prediction horizon, which corresponds to 1 hour prediction, we are going to have 3900 by 3900 matrix for the whole sigma, for the whole covariance matrix, which is not possible to compute over and over again. So to address this challenge, I propose two kind of solutions. First one is we decompose the full covariance matrix into smaller covariance matrices by using Kronecker product. So intuitively, we can assume that the whole NQ by NQ covariance matrix can be decomposed into temporal covariance matrix and spatial covariance matrix, and the whole covariance is the Kronecker product of temporal and spatial covariance matrices. And then because we know that the sigma, the covariance matrix, is a positive semi-definite matrices, and the inverse of covariance, which is the precision matrices, are also positive semi-definite matrices, we can parameterize the inverse of covariance or precision matrix with Cholesky decomposition. And by doing so, we have some kind of benefits in the calculation because the lower triangular matrices, to compute the determinant of the lower triangular matrices, we can just simply multiply everything on the diagonal. So to kind of review what we did, so we had the original equation. By introducing the Kronecker product, we can we are assuming that this covariance, the whole covariance matrix is following the Kronecker product. So we can derive this from this assumption. And then we can further reduce the computation by introducing the Cholesky factors for the precision matrix. So this is how usually traffic forecasting goes for deterministic setting. So we have input, we have model, we have output, and then we compare the output with target, and then we compute the MSE or MAE loss. So in my case, in my model case, so we have several more things here, but this output is the same. We have one more neural network that computes the omega t, which is the mixture weight. And then this LSLQ, which kind of calculates the covariance matrix, exists outside of this neural network. And then we can train everything all together by using the negative log likelihood. I tested the model with PAM-based data, and I actually did with other data set as well. I'm showing the results for PAM-based data. And I used Graph WaveNet and SDGCN, which is also another widely used traffic forecasting model. And by just replacing the loss function, we get 5 to 12% performance improvement. And then what I found was that, so the performance improvement was more effective on the long-term forecasting, which in 60-minute prediction, compared to short-term prediction, which is 15-minute prediction. And this is also intuitive because we expect that in short-term setting, we can kind of assume that everything is independent. But as we predict longer, further in the future, we expect to have more spatially or temporally correlated structure in the covariance matrix. So this model actually gives that kind of reasoning of incorporating the spatial temporally correlated structure in traffic data. And then by incorporating that characteristic, we can further improve the model, even though we didn't really change much from the neural network side. Okay. So as I mentioned, because we set this omega t to be time varying and sigma q and sigma n to be fixed over time, we can visualize what the model actually learned during the training process, and then we can visualize how they work in the testing data set. So first figure here shows the mixture weight over time. And the second figure over there shows the covariance matrices for each mixture component. For this experiment, I used 3 components. So the large capital K over there is equal to 3. So here, what we can observe is that this first component, which is the blue line here, kind of explains how the spatial temporally correlated structures work in peak hours, because they are dominant from 6 a.m. to 9 a.m. and around 3 p.m. to 6 p.m. And then we can kind of expect this green line here, the third component, kind of explains the free flow state because they are dominant during the night. And then they have some kind of half dominance during the afternoon of peak hour. And if you look at the covariance matrices, the first component on the top kind of shows strong spatially and temporally correlated structure. And that makes sense because the first component is trying to explain how the congested states work. And we expect that the congested, more and more we have the congestion, more and more the traffic data or traffic is going to be correlated spatially and temporally. And the third component here and the third component, the covariance matrices for the third component on the bottom kind of shows some kind of independent spatial covariance because we don't really have much data of diagonal. So we can say that in free flow, everything in spatially, so everything is uncorrelated spatially, but we still do have some kind of temporally correlated structure. And that also makes sense because temporally we expect some kind of relation. So eventually this whole modeling framework kind of offers this interpretability of the neural network. And then after training, after doing some kind of evaluation, and after doing some testing, we can get this kind of reasoning of what the model actually learned through the data. So this dynamic mixture model, by using this objective function to train traffic forecasting, kind of offers a way to model the time varying distribution of strongly spatial temporally correlated data, which is traffic data is one example. And I expect that this can be generalized to different spatial temporal data, including weather and sea surface temperature. Right now, I'm working on sea surface temperature data to see if I can further improve the state-of-the-art sea surface temperature model, prediction models by incorporating some kind of spatial temporally correlated structures. Okay, that was it for the first part. The second part I'm going to introduce is generative trajectory analytics. So here I'm going to introduce, it's not new anymore, but new type of data called trajectory data or mobility trajectory data or vehicle trajectory data. And then how I try to reproduce new trajectory data by using a method called deep generative models. So mobility trajectory data is a type of data that describes the movement of different agents in the city, including vehicles and pedestrians. And this type of data is easily collected thanks to many different location sensors and communication devices, such as GPS, Bluetooth, Wi-Fi, smart cards. So when we look at this individual trajectory, one individual trajectory describes where this person came from, where this person is heading to, and it also describes which route this person took or how much travel time it took to get to the destination. But then when we take the group of trajectories, when we collect a large, massive amount of group of trajectories, this whole group of trajectories actually represent the overall mobility pattern in the city, describing vehicle movement, population density, flow, inter-regional flows, and OD distributions, and so on. So one of the things I was interested in was to how can we model this large complex trajectory data which has spatial temporal features by using neural network and generative models. So this ability to reproduce trajectories of individual agents have been studied by transportation engineers for many years. So the problem I'm trying to solve is not very new. But what they did is that because they could not really observe this through trajectory data, they assumed some kind of model. So they assume by inputting network topology and some kind of model parameters and some behavioral assumptions, they use, people use trip generation to get OD, route choice models, and simulation to output the simulated trajectories. And they hope that these simulated trajectories can actually have the mobility patterns in the unobserved trajectories. But they do have some kind of limitations, such as complex model building and calibration processes, and strong behavioral assumptions, and simplified physical process models. But now we can actually observe large amount of trajectory data. And then we've seen a lot of great advancements of computing technologies and data-driven and machine learning-based models. The question I asked was, can we actually train some kind of neural network that can generate realistic trajectories by just inputting the observed trajectory data set as input and then get the generated synthetic virtual trajectories as output? And then that was the main question. One of the main questions I asked during my PhD. And then I also worked with great team, Professor Hwasu Yoo from KAIST, who is my PhD supervisor, and Professor Ji-won Kim from the University of Queensland. So to kind of briefly give you some idea what this deep generative model or generative model is, so the goal of generative model is that given training data drawn from some distribution, we call the distribution P data X. And we want to learn a model that either directly models the P model X that's similar to the P data X, or a model that can generate new samples from the same distribution. And so the last 10 years, I would say, was the breakthrough. So one decade that kind of had some kind of breakthroughs in deep generative model. And nowadays we usually have these three types of generative model: generative adversarial networks, normalizing flows, and diffusion model. So the first topic I'm going to cover in this part 2, I'm going to use I use the generative adversarial network as my modeling framework. So this is my model that reproduces realistic synthetic trajectories. It looks kind of complicated, but actually this can be divided into two parts. So one is RNN and one is Gale. I'm going to cover what that is in the later slides. So predicting or generating trajectories was also studied in previous researchers, but what they usually did was that by inputting the sequence of previously visited locations, they predict the future trajectories. And usually they use RNN sequence model, but nowadays there are more advanced sequence models that's available. So the model part we can replace. But then the problem setting itself is that has some kind of problem that, so as we go, and the small amount of error at each prediction step will accumulate and have a big difference as a whole trajectory. So we need to kind of incorporate some kind of distribution of expected future trajectories, which I call multimodality of trajectory data. But if we don't consider the previously previously visited locations, the generated trajectories would not really make sense. So what this model actually does is that we use RNN to kind of embed or encode the sequence of previously visited locations. And we use generative adversarial imitation learning to model the distribution of expected future trajectories. So now we can see that the upper left part here kind of represent the RNN part that encodes the previously visited location. And the lower right part, the bigger part, represent the GALE, which is generative adversarial imitation learning. So imitation learning is also known as learning from demonstration. So when we give expert demonstration as real-world data, the objective of training is to train an agent that mimics the behaviors of the expert. So in the early days, this imitation learning was used to teach robots to perform certain tasks. So by giving human demonstration of picking up something, the robots can learn to pick up something and so on. And then the application area has been expanded to human behavior modeling. So here the input is how people actually behaved or how people decide some kind of task, and then we are trying to model their decision process that's in the data. And GALE, generative adversarial imitation learning, is a combination of imitation learning and generative adversarial network. So we have this generator that generates samples, and then this discriminator kind of compares the generated samples with real samples, and then tries to distinguish the generated samples from the real samples. So as there's a competition between generator and discriminator goes on, eventually we are going to have a strong generator and strong discriminator, and this strong generator would generate realistic samples that we expect or we can see from the real data. So I know it's kind of confusing, so let me kind of briefly review what this is. So as agent, we have a vehicle choosing its routes. So this is a Gangnam network, Gangnam district in Seoul, South Korea. We have this road network. So we have our agent, individual vehicle, as our agent, and it's traveling in this network. The state of this agent is the current and previously visited locations. And the action is this, the link-to-link transition movement, which can be defined as going straight, turn left, turn right, or terminate the trip. And then we give urban vehicle trajectory data or mobility trajectory data as our expert demonstration. And then the goal is to generate realistic trajectories that has the same or similar mobility patterns that was in the training data set. And then I use some simulation-based generated data, which I took from Aimsun. And then I used a Gangnam data set to verify that that actually works in the real-world data set. And in evaluating how this works, so when we generate new trajectories, we expect the individual trajectories to be realistic, so that meaning that the generated trajectories should have the same properties with the real individual trajectory, but also as a data set as a whole should have some kind of realistic pattern. So when we generate large amount of trajectory data from this model and have some kind of generated data set, this generated data set should have some similar pattern that we can observe from the real data set. So I divided the evaluation into two parts. First one was trajectory level evaluation. The second one was data set level evaluation. So in trajectory level evaluation, I used two trajectory synthesis score. I took it from natural language processing. The scores are BLUE and METEOR. So it's higher the better. So higher the bar is, the better the performance. Here we can see that our model, which is in purple, kind of gives better performance compared to other model. So actually in the real world data set, the proposed model gave 6 to 23% performance improvement compared to the state of the art in 2021. And also what this model offered was that the standard deviation of the scores was much less than the other models, meaning that the model can generate realistic trajectories in stable manner. So it doesn't really go beyond some threshold. It can generate really good individual trajectory stably. And then in data set level evaluation, I used Jensen-Shannon distance, which measures the distance between two data distribution. And even though the complexity of data set increases, we don't really lose much in traj scale. Compared to other models, which kind of performs bad when the complexity of data set increases, the proposed traj scale model offers much stable outputs. So to kind of summarize this part, trajectory data provides novel insights in understanding traffic system from individual mobility behavior. And the proposed model traj scale offers a fully data-driven alternative to traditional models for generating urban trajectories or mobility trajectories. So this work was, the objective of this work is to understand the distribution of network level vehicle trajectories. And then after I graduated my PhD, and so when I did my postdoc and as a side project, I kind of got interested in how can we can model the network level vehicle trajectories, but can we do the same thing for more microscopic vehicle trajectories too? So this kind of microscopic vehicle trajectories or microscopic, not vehicle, so agent trajectories or mobility trajectories, we can easily collect this kind of data thanks to computer vision and object tracking methods that's available open source nowadays. And it kind of helps us to understand driving behavior, for example, of NGSIM data, or pedestrian movement in Stanford data, or some kind of vehicle to bicycle or vehicle to pedestrian interactions based on this INDI data. So one of the research questions I'm kind of dealing with right now is that, can we predict or model the distribution of future trajectory of individual agent? And there has been a lot of work on this area too. And usually what they do is that same for traffic forecasting, based on some kind of previous GPS location or previous locations, they predict the deterministic trajectory in the future. But in trajectory data, we really know that future trajectory data have some kind of multimodality. So I'm trying to model the distribution of future trajectory given the past trajectory. So again, we have a lot of different generative model nowadays. In this case, I'm using a model called normalizing flows, which kind of gives us explicit density, which means that we can model the distribution itself directly. So the basic concept of normalizing flows is that if we want to model this complex PX that cannot be modeled by some assumed distribution like Gaussian distribution or other distribution, instead of directly modeling PX, we can start from simple distribution, usually uniform distribution or Gaussian distribution, and then we can learn the transformation from this distribution to that distribution. And by learning that transformation, we can use the change of variable theorem and then directly model the PX by using this equation. And this gives a lot better understanding of the distribution compared to other modeling framework such as VAE, variation autoencoder, or again, generative adversarial networks, because it explicitly, directly try to model the log likelihood of the data distribution. So one of the ideas I have right now is that because we have the coordinates and some kind of features such as speed, acceleration, and heading and class of the agent, we can build some kind of encoder, that condition encoder, using RNNs or transformers or other types of neural network. And then we can feed that information into normalizing flow so that we can model the conditional distribution of future trajectory based on our observation and the features we have for the specific agents. And one of the applications I have right now is that we can predict the vehicle trajectory, microscopic vehicle trajectory in intersection. So here, the blue line here and blue line here are the given trajectory, which is about 4 seconds. So I have 0.04 second as time resolution. So I have 100 data as input. And this red line here is another 4 seconds in the future. So the model really doesn't know that. But this model actually can fit some kind of distribution that kind of matches with the red line. And another interesting thing about this video right here is that at the longer prediction stage, we do have some kind of density right here. Because we only have this information as that's given to the model, this can actually represent some kind of going straight behavior too, when we have large amount of data. So this model actually can kind of have that, can kind of model that kind of multimodality in the data set by directly modeling the log likelihood of the data. And I expect I can use it for monitoring the intersection safety. And then I can model the interaction between agents. So consider when we have multiple agents and consider when we have the distribution, the future distribution of multiple agents, we can simply kind of overlap those two distributions and kind of calculate the conflict probability between these two agents. And then by doing so, we can model how they react to those kind of conflicts to avoid the traffic pedestrian vehicle crashes or vehicle-to-vehicle crashes. Another example, another application I have right now is that, so we can use the same framework for predictive airspace allocation for urban air mobility. So the map here right here is, so we have Seoul, South Korea right here. There's a large airport called Incheon Airport right here, but we do also have a smaller airport right here called Gimpo Airport. So the South Korean government is trying to build some air taxi system, so air taxi service in South Korea, coming from Incheon Airport to somewhere in Seoul. But since we have a lot of airplanes, aircrafts passing through this zone in between, we have a lot of, we expect a lot of conflict between these air taxis or UAMs and conventional aircraft or airplanes. So the idea was to predict the future distribution of this conventional aircraft because they do have a lot of uncertainties, especially near terminal airspace. We can predict the future traffic, future trajectories of those aircraft. So right here, we have the red one as input, blue one as the future state. We have the green dots, which are the samples from the distribution. And then by feeding this information to the control system, we can design some kind of control logics for UAMs that we can effectively avoid the crash between, not crash, so conflict between between UAM and aircraft, conventional aircraft. So this second topic in generative trajectory analytics kind of gives some potential, provides some ideas or potentials of conditional normalizing flows for predicting distribution of future trajectories. So we are doing some kind of density estimation for trajectory, and we want to use the predicted information to have some kind of predictive decision making. And right now, I do have 2 applications that I just introduced, but the potential of this work can be generalized to other trajectory data or even other data set. So I'm imagining how this work in the future. So to kind of conclude my presentation, I want to briefly introduce my future research goal in one slide. So my overall goal is to enhance the understanding of human mobility and traffic system by modeling the distribution of complex traffic and mobility data. And then I want to develop or provide better decision support tools for both individual users of the mobility network or traffic network, as well as the system operators like government or traffic operations centers, something like that. And in doing so, I want to have some kind of probabilistic decision-making process that kind of enables us to make better decisions based on the given information we have. And so these are my research core. I have some keywords that I'm going to focus in the next 2 to 3 years. The first one is explainability and interpretability of the neural network or the model I'm developing, and the scalability. So when we have more and more sensors and more agents in the scene, how can we scale the computation, or how can you scale it to 1 million or 1 billion sensors, something like that. Also, I want to focus on how can we model the interaction between agents or interaction between agent and the system, and how can you use the system level data to make to have better decision making for individuals, or how can you use the individual data, data from individuals to have better decision making for in the perspective of system operator. So thank you. This is it for my presentation. If you have any questions, please ask. Yep.
Well, does anybody have a question for Seongjin?
I can feel the heart coming in.
I want to go back to the first part.
Okay.
Okay. And your assumption that your correlation or covariance matrix is static, and that bothers me a lot.
Okay. Yeah.
In particular, did you just look at morning data, do the full fit for all the parameters, and just look at the evening data and do a full fit, and then compare the two correlations or covariance matrices to justify that assumption of them being static?
So the covariance matrix here is static, but we have multiple covariance matrices, right? So I've looked into the data, and then if we have one model for 2 to 3 a.m., one model for 3 to 4 a.m., then I can fit it into one Gaussian distribution with one covariance matrix. And naturally, if the time differs like 2 to 3 to like afternoon 4 to 5, 5 to 6, they have different covariance matrix. So because we have this mixture of components, even though we have the fixed covariance matrix, we can control the dynamic part of the covariance. So I know what you're asking, and I've tried to model the time varying covariance as well, and that actually worked too. But what I wanted to have was some kind of modeling framework that improves the model, as well as giving some kind of interpretability and explainability so that we can understand what it's trying to do. But when I model the sigma covariance matrix and make it time varying, we lose the interpretability because we cannot actually track how this model is actually modeling the covariance or correlated structures because it's changing too fast. And we had some issues about overfitting the correlated structures. So we decided to keep the component covariance matrix to be fixed over time, and then control the dynamicity or the time varying part by controlling the mixture weight.
Okay, well, I'm going to butt in and ask a question here. And that is, when one's trying to predict a trajectory.
Yep.
All right, it's fairly well known that you get a real advantage if you happen to know where the individual is going.
Right, right.
And it seemed like you're doing without destination-specific information. And so how do you manage to pull that off?
So that's a really good question. And so if we know where this person is going, if we know the destination in network trajectory, or if we know the exact point that, if we know a person is turning left or going straight, we can definitely have better prediction. But in the real-time traffic monitoring or real-time traffic management sense, we don't really have that information. So eventually, the reason why I'm trying to develop complex models to fit the distribution of trajectory data or traffic data is that I want to kind of have some kind of downstream task that can be used in the real world, application. And one of the things I want to develop is real-time monitoring. And if I consider something I cannot collect in real time, then the model in the upstream part doesn't really satisfy the needs in the downstream. So that's why I didn't really put it. But so there are many modeling frameworks that first predicts the goal state, which means that predicts the future state first, and then try to predict the trajectory. So there's a modeling like that, or we can do, so in microscopic trajectory setting, some people also use mixture of Gaussian distribution, meaning that each component kind of explains turning left, going straight, or turning right movement, something like that. So there are many ways we can accomplish what you said. Right now, what I'm focusing is that if we don't have the information, so even though we don't have the information, we should be able to predict or generate that kind of trajectories.
Okay.
Okay, so for your intersection trajectory prediction, so all the possible movements that a vehicle can take should be restricted by the intersection geometry.
Right.
I'm wondering if you have taken that into consideration. Oh, sorry, geometry and the intersection movement.
Yep. So the short answer is no right now.
Okay.
But I expect that I am going to do that in the future. So right now, so there are many settings for this same problem too. So right now, what I'm doing is I'm assuming that I have a fixed location sensor, and then I can collect trajectories at this intersection. And we expect that the data should have some information about the geometry, because we can have vehicle passing here in real world, but we expect it to be outliers. So we have more trajectories on the vehicle on the road compared to the sidewalk and other parts. So from the data, we can actually get those kind of things, but there are many ways we can restrict the distribution to be within the road geometry and within the turning movement. And especially, so in terms of turning movement, so in traffic simulation, we expect that people turn perfectly. So people turn kind of in perfect trajectory, but in real world setting, we all know that we don't really turn perfect trajectory. So I think it's better to use the raw trajectory data to extract how people actually turn and how they actually have the driving manual. And in some studies that uses the autonomous vehicle data, they usually try to incorporate the geometry of the road, because in that setting, the car is moving around and they will have different road geometry at each prediction time. So in that case, those models try to incorporate the road geometry and then try to restrict the prediction within the road. So there are many ways we can model that kind of thing.
Okay, thank you.
Maybe time for one or two more.
It's kind of the following question of Dr. Davis' question. How much for the trajectory predictor, how much your network, your predictor is robust? Because one of the most common problem among data set is that they're not perfect. We have some missing data. And also you mentioned that you want to cover a multi-agent trajectory. And another problem is that you conclude, okay, long-term prediction is give us better performance. So like, is it your, like, the result will be more vulnerable because you want to predict long-term?
So that's also really good question, and that's something I am kind of trying to do right now. So in this setting, so I just have the preliminary results right here, but in this setting, we kind of assume that we have at least we have the perfect information for the trajectory, and thus so location and speed. So right here, I didn't really cover how the model is going to perform when we have missing data. And when we have some kind of anomalous, so noisy data that's input to the predictor. But I think there are many ways that we can deal with that. Also, so I'm using normalizing flows, but nowadays diffusion models, they have some capability of, after training the P data X by using diffusion model, we can easily fill in the missing part without retraining and by using some kind of simple logic in the diffusion process. So that's another topic that I'm kind of doing right now. And about the vulnerability. So right now, since I assume that the information I have for the blue parts are perfect, so I expect that the prediction performance will drop if they have some kind of noisy or missing part. But by incorporating those kind of like imputation or curve fitting or more robust modeling of the inputs, I think we can have some more accurate, robust trajectory predictors later on.
Okay, one last question.
Yeah, very interesting talk. I just have one. I'm just curious, how big is your data set? Because I think there are a lot of similarity between traffic flow and geophysical flow. Like I trace sediment trajectories all the time. I wonder if your methods can apply to my fields to predict erosion, transport.
So I think, so for traffic data, usually people use about 4 months to 5 months data, and then for training, and then use one last month for testing. For the urban vehicle trajectory data used here, I had about 1 year of taxi trajectories that's collected from Seoul, South Korea, and I extracted the parts in Gangnam district, and that made about 400K trajectories total. And for this work right here that I did with the intersection vehicle trajectory, I think this one only had about 10K trajectories. So usually it's more the better, bigger the better. But nowadays, people say better the better. So nowadays, it's easy to collect more data. So it's getting cheaper and cheaper to collect this kind of data or other types of data. So we have big data, but it's better to have better data. So good data in the data set that actually explains how this kind of distribution works. And that kind of enables, that kind of enhances the training process. So if you have, even though you have a small amount of data, some people use simulated data on top of the real data and then try to fit the whole data and then try to focus more on the real data. And there are many ways we can augment the small amount of data to big data and then train the neural network. So I think we can talk later about how it can be combined to your work and other applications. And I'm really interested in using same methodologies for many other civil engineering applications.
Thanks.